Now, we've been talking about groups as mathematical objects, and we often use mathematical objects to build more complicated mathematical objects. For instance, we built the complex numbers out of the real numbers. We built the real numbers out of the rational numbers, built the rational numbers out of the integers. Here we're going to use groups to build more complicated groups through this operation called direct product. Now, we've seen this before. Basically, direct product of two groups is you create a set of ordered pairs where the first number in the pair is from G and the second element from the pair is in H. Now, interesting thing about direct products is that we can use this same idea to decompose groups. Sometimes you may have an existing group that can be considered as the direct product of two of its subgroups. So we're going to work this both ways. We're going to show how to build up larger groups from smaller groups, and we're going to show how to analyze large groups in terms of this direct product structure. And we'll end up with a very nice theorem that shows us exactly what all abelian groups look like. Okay. All right, so now, in this first endeavor, where we're going to build up new groups, this is called external direct product. So given two existing groups with two possibly different operations, we can define a new group called G cross H. It consists of pairs where the first item is in G, second item is in H, and the group operation in this larger group is defined as follows. Here I'm just writing the two group elements next to each other. That means this group element, G1H1, operating on G2H2, is given by, well, operate the first components together, operate the second components together. Okay, so typically we'll write this way, understanding that the group operation here is for G, the group operation here is for H. Okay. Now it turns out that this construction does in fact give me a group, and that's this next proposition, and that's something that you will be proving. And here we have R2, the under addition is actually a direct product of R with R. And some more examples of direct products. We talked about direct product of two groups. We can do direct product of multiple groups in the same way. Just the same thing you did with multiplication. Once you define multiplication of two numbers, you can define multiplication of an arbitrary number of numbers. This particular group called Z2n is the direct product of n copies of Z2, and it's very important in coding theory. Okay, now let's consider some properties of direct product. In particular, we know that group elements have an order. Suppose we take one element of group big G and one element of group big H, and we know the orders of these two individual group elements. What's the order of G comma H in this big group G cross H? Well, it turns out that the order of G comma H is the least common multiple of R and of the individual orders. And here's a proof here of how that works. We kind of saw a similar thing with permutations. Remember what we had a 2-cycle and a 3-cycle. Remember what the order was. Well, the order was 6 because this has order 2, this has order 3. The least common multiple is 6. So this is really the very same thing we saw in permutations in a more general context. And we have this similar corollary that if you have a product of group elements in different groups, then the order of the external direct product is the least common multiple of the individual orders. This was the same thing when we have permutations, multiple cycles. The order of a permutation is the least common multiple of the orders of all of its cycles. Okay, more examples here. All right, so we use this to show a particular isomorphism. Suppose we have Zm and Zn, two additive groups of integers mod m, integers mod n. Okay. And it turns out that you can define an isomorphism between this group and Zmn if and only if the GCD of m and n is equal to 1. Okay. Now remember, in Zm you have 1 up to m minus 1. I'm sorry, it's 0 up to m minus 1. In Zn, you have 0 up to n minus 1. Now, if you take the direct product of these two, well, how many elements does it have? Well, I can take any one of m elements here. I can take any one of n elements here. The order is going to be equal to m times n. So these orders do match up. The problem is that doesn't necessarily mean that they're isomorphic. We know that this group is cyclic. Okay. We don't know whether this group is cyclic. And it turns out that this group is cyclic if and only if the GCD of m and n is equal to 1. And it turns out also that the generator for this group is the element 1, 1. So that's the way the proof goes. We show that if the GCD of m and n is 1, then this element 1, 1 has order mn if the GCD of mn is equal to 1. In fact, the order of 1, 1 turns out always to be the least common multiple of m and n. And that's equal to mn if GCD is equal to 1. So that's what this proof goes through. Okay, so we do the same thing with multiple products of integers of different moduli. And we can actually do the same thing for primes. It's a special case of the previous result. And what happens is that now we get a very beautiful result for abelian groups. Abelian groups are kind of like permutation groups where you have disjoint cycles. And it turns out that any abelian group can be written as isomorphic to an external direct product of copies of integers mod primes. So you can decompose any group into these factors, where each factor is an integer mod n, and the n is a power of a prime. Okay, this is kind of like prime factorization of numbers. Very similar idea that you can divide a number into factors. Now it turns out that you can divide a abelian group into what you could call prime factors, but these are powers of primes. Now it's possible you could have, for instance, you could have zp squared cross zp. That's an abelian group. They don't have to be distinct. I could have, for instance, I could have z9 cross z3. That's an abelian group. And that falls into this classification. Now we're not actually going to prove it, but you can see the logical progression of how that would work. Okay. So we've talked about how to build up larger groups from smaller groups. Now we're going to show how to recognize when a group can be broken up into two smaller groups. Okay. So let's consider a group G, and suppose it has two subgroups with the following properties. That G is equal to set H times set K. What that means is that I can express any element of the big group G as a product of an element in big H times an element in big K. Now there might be more than one way to express it, but it is possible to express G as a product of group elements in this way. Now notice that G is not necessarily abelian. However, all right, so let's go on. All right, so we're also supposing that in this particular group, H and K are distinct. So here we have our group G. We have H and K in here, and the only intersection they have is the identity. So here's H and here's K. And the final condition is that every element of group H commutes with every element of group K. So an element in here and an element in here, these two elements commute. Now that doesn't mean that any two elements in the group commute. It just means that every element in this set H must commute with every element in this set K. It turns out that in this case, G we define G to be the internal direct product of H and K. I'm going to go through a few examples of this construction. And the important thing is that, in fact, if G is the internal direct product of two of its subgroups, then in fact G is isomorphic to H cross K. So in other words, G can be identified as the direct product of two of its subgroups. All right, so we prove this as usual by trying to define a mapping from G to H cross K. And then the proof consists of showing that this is actually a bijection and that it preserves the operation. So you can go through those steps in the proof here. And then here's some more examples to illustrate the concept. And here we kind of take that proposition backwards. It says that if G is isomorphic to an external direct product of two of its subgroups, then G is in fact the internal direct product. So we're just identifying internal and external direct product as basically the same thing. As before, we can extend internal direct product to a product of multiple subgroups, and we get the same result, that if you can write G as the internal if G is the internal direct product of multiple subgroups, then G is actually isomorphic to the external direct product of these subgroups. And that finishes our video on our section on isomorphisms.